All right. So, can everybody read what that says?
Yep.
Okay, good. Turn Island Systems. Turn Island Systems is a company that Steve over there, Steve Roberts, and for RVE, and I started, I don't know, year and a half ago, maybe longer. Steve and I are we're sort of separated at birth, except we took vastly different paths after we were born. So, but we found ourselves, discovered each other some time ago on a sailing forum talking about electronics. And turned out he and I had both moved to the same island. So, started doing some fun stuff together. One of the things, hate to admit it, still haven't finished it, is a drift buoy, something that would send a beacon and just float around in the ocean. Lots of people doing it. I thought, well, we could do one and it would be even better. But so in the process, ended up with a lot of interesting things. So here, okay, here's a picture. You see my cursor moving around on the screen there?
Yes, we do.
Okay, that's me. If you go to Wikipedia, type in Telecom Valley, you will find I am the poster child for Telecom Valley for some reason. Somebody found an old picture of me probing, I don't know, probably a T1 board or something. That was some time ago, but I've been involved in electronics ever since elementary school, really. And I retired some time ago, kind of early, for good reasons. And but now I still can't kick the habit, so still do this stuff. And Steve, he does recumbent bicycle stuff, and he's still, as I say, still tech, maybe a little bit less nomad. But we're having a lot of fun doing this Turn Island System stuff. Let's see what's on. I don't have things prepared, but I did put pictures kind of in order to remind me what to talk about. One of the first things we did is in Turn Island. I wanted to study the frequency stability of my drift buoy, and my old Hewlett-Packard frequency counter with the Nixie tubes on it was crapping out. And looking at what I wanted to do with the frequency counter, I just couldn't see myself spending all the money for a fancy frequency counter. So I went and designed one of my own. It's a time interval counter, 10 megahertz reference clock, 100 megahertz PLL inside. Most of this stuff, it's really a little bit of analog front end stuff and a little microcontroller, which is essentially a also an Arduino style, but it's on the board. I put the chip on the board but sort of clone the design, and it's got an FPGA that does all the heavy lifting.
Where do you get your 10 megahertz source, Paul?
I've got two sources. One is there's a jack on the back to an SMA. That's an external 10 megahertz input, so that would nominally come from a GPS-DO, GPS stabilized oscillator, or an OCXO or whatever. Internally, I've got a TCXO, just a fairly garden variety TCXO. It's adequate for most use, but if you want to be really precise and stable, then you feed an external clock into it. And I'll talk a little bit more about that pretty soon, I think. The other thing was I liked I don't know if you're familiar with the SI5351. It's kind of like the go-to synthesizer chip for so many radios and lots of other stuff. It's got two PLLs in it. It'll take an external reference. PLL typically runs between 500 to 900 megahertz, and then it's got fractional dividers. Don't get me started on fractional dividers because I love those things. I'll talk for hours about them. But it's got fractional dividers on the PLL phase lock feedback loop. Also, it has three outputs with their own fractional dividers. And so the chip will put out anywhere from, I don't know, it's like 8 kilohertz or something, all the way up to, over 100 megahertz with amazing frequency precision. I mean, it's got to be factors of rational numbers, but the way it's designed, you can get pretty amazing stuff. So I designed this clock box. I put an SI5351 in it, put the 10 megahertz reference on the back if I wanted it, internal OCXO, and then had buffers for the outputs. So I'm trying not to talk too much here about it. But if there are questions, I'll go on and on. So in the process, there's a radio called the QDX, QRP Labs QDX. If you're not familiar with it, check it out. It's pretty amazing. And Hans, the guy that runs QRP Labs, even has a newer one that'll do sideband, I believe. I haven't played with it myself. But this is a digital transceiver, audio in. I won't go on and on about it, but it's really cool. You should check it out. So I was hanging out on the QRP Labs forum on the internet, discussing that transceiver. We were talking about frequency stability issues. For most modes, the QDX is just fine, but some of the, even Whisper, and then the slower digital modes, like the FST4W modes, the thing just has too much drift. So we're looking at ways to stabilize it. And I spent a lot of time on the internet with Hans. Again, Hans, the guy that owns QRP Labs, and really couldn't figure out a good way to stabilize the oscillator on the board. There are just too many thermal issues. So I designed an external clock adapter for that. Either a direct 25 megahertz input, or I have another board that's a clock multiplier. Feed it 10 megahertz or 5 megahertz, and it multiplies it up to 25 megs, which is what the QDX needs internally. Turned out I had a 10 to 25 megahertz multiplier in an earlier version of my clock box. That's the one with the SI5351. So I was able to repurpose that design. And I'm talking about this, these different modes, and turned out, I learned about FST4W and the ionospheric propagation research. And I've got links for that if you're curious. And I'd already turned the clock box into a Whisper beacon just because it was fun. So, and turned out they needed, for this research, they needed a multi-band transmitter. So I figured, hey, how hard could it possibly be to modify my design, turn it into a 6-channel beacon? Well, actually, the design was pretty easy, but the implementation is, well, we can go on. Here's the time interval counter internals. I got 4 input stages. The stuff in blue or light blue is what's inside the FPGA, and there's a little bit of partitioning here that's not quite right, but this just shows the essence of it. Cool thing that I added late in this, and wonderful thing about FPGAs, is I didn't have to even change the board layout. I had a numerically controlled oscillator and a digital mixer inside, and a digital filter. So now I can take an input signal, I can mix it down in frequency down to 10 hertz or 100 hertz or something, and get amazing effective precision quickly. Here I'm showing what my time interval counter is doing with FST4W QRP Labs transmitter. You'll notice this is the modulation, but you notice the drift starts transmitting a temperature, the frequency goes up a little bit, then it goes down and it slowly stabilizes. And 30, 21, 30. This is this is over half an hour from start to finish, roughly. Question?
Is the thermal drift a result of the transmitting and then heating up?
Yes. Yes,
Okay.
The output final stage, which is 4 TO92 FET transistors. They put out enough, they're only about, they're not much better than 50% efficient. It's a class D output because it's a broadband at that stage. And it puts out a fair amount of heat, which propagates across the circuit board and inside the cabinet, just air temperature, but I think it's mostly circuit board. And then that gets over to the, it's a good TCXO, but even a good TXO isn't good enough for this stability. It's a fraction of a hertz. It's drifting a couple hertz, but that's way more. You could not decode this signal. The drift has to be less than a symbol width or frequency shift, and here the drift is way more than that. So with my fancy time interval counter, I can get, basically I can get better than 100 microhertz, 1.1 millihertz frequency resolution of a 10 megahertz signal, sampling that signal, getting samples at 100 hertz rate. So that's okay. You can buy other frequency counters that'll do this, but you got to spend big bucks for them. So I was happy with that. And here you can measure. This is what you can do with that counter. Here I'm measuring again the QDX TCXO. This is I had the thing in a temperature chamber, a modified thing that they call a reptile incubator, but of course it's a thermoelectric cooler. I built a controller to control that thing, and then software to control the controller. So now you can see the frequency drift as the temperature goes 10 degrees up to close to 50 degrees centigrade, drifts up and down again. But you notice it's got what's called retrace. In one direction, it's high, coming back down, going cold. I think that's one direction it's high, the other direction it's low. And then you go to small frequency variations, you get the same sort of thing. It's not a single line, which is something that many people, I did not initially know what was causing that. It's an effect called retrace. If you go to my WB6CXC.com blog, I think I have some presentations on this, so I won't. But anyway, so you can make really precise measurements, and it came in really handy in figuring out what was going on at the QDX. Here we go. So, okay, out of that, Turn Island Systems developed our clock reference interfaces. Here's one 25 megahertz input. It's really just input protection. Then it goes off and it feeds the oscillator buffer on the board, on the QDX board. Here's one with a little phase lock loop multiplier. It steals 3.3 volts from the QDX and puts out 25 megahertz. You can, if you have a 5 megahertz, yes, go ahead.
Just to be clear, these are mods to the QDX.
Yeah, I don't have a picture of it with me here now, but you can replace. I also came up with a replacement back panel for the QDX with a hole in it for this SMA jack, and I managed to shoehorn everything in. So the only mod you have to make to the QDX is you have to remove one capacitor off the board. It's a service mount capacitor, so you gotta, have some finesse when you're doing it, and then solder these wires. Fortunately, there were through holes that I could use for the power wires. This twisted pair here, the small one is the 25 megahertz clock. I'm able to feed those two wires through a through hole to get to the other side of the QDX board. Again, I've got a documentation on these clock interfaces on the Turn Island Systems website if anyone's interested in the details. I think I got a schematic on there and everything. Okay, so yeah, here's the clock box. I already talked about that. But it's something that I use myself. Haven't tried to sell it yet because I'm not happy with the kind of user interface software. I mean, that's the hard part, is getting the software. I can drive the thing, but I wouldn't want to inflict it on anyone else at the moment. So clock box to Beacon Blaster, more Turn Island System stuff. The Beacon Blaster, as I mentioned, is a 6-channel transmitter, and we kind of went back and forth on, well, what do we want this thing to look like? What are the requirements? What do we include inside the box? What do we put outside the box? And finally I decided that, okay, I've got two SI 5351s there. Had to learn, is that show? So we talked to, I had to learn how to, these things use a I2C interface, and they only have one I2C address. So I had to come up with a multiplexing scheme. And you can buy I2C multiplexers, but to control those, you need to use I2C, and there's a whole protocol. And I needed to switch these things really quickly. So turns out an analog switch does a really good job of multiplexing. So I had to figure that out. Here's my external 10 megahertz reference, because you really want a stable clock when you're doing a FST4W. I stuck a GPS module on there, one of these, not an integrated circuit, but it's a little module that solders down to the board. So GPS antenna in, I put a GPS splitter, just a passive resistive splitter. So the antenna connects here. This powers the antenna, a little puck antenna with that gets its power from this GPS chip. But then it splits and goes out of here. And typically what I do is I run that output, connect it to a GPS disciplined oscillator. That way we only need to use one antenna and we can share it. There are other ways to split a GPS antenna signal, but thought I'd throw it on the board. So I'm using a Bodnar, BODNAR GPS disciplined oscillator. It's a really good one. They're inexpensive, relatively inexpensive. And that's typically what we're using with this Beacon Blaster. So there's the little processor here, USB port for controlling it, and external power connections. And then these are the six outputs going through a buffer from the SI5351. And every one of these is identical. You can put them all in the same frequency. You can pick any frequency in the ham bands or out of the ham bands if you want to do some special configuration. But typically, it'll be 80, 40, 30, 20, 15, and 10 meters, but it can be anything. So this is completely frequency agnostic inside here. These things then feed a 1 watt digital amplifier. And actually, I'm not inside the box. I'm not using these SMA connectors. I see these little tiny, they're called U.FL connectors. So for like less than $1 each, you can get a cable that snaps onto that connector, then snaps onto this connector. This is my amplifier board. And again, this amplifier board is frequency agnostic, but it puts out about a 1 watt square wave into 50 ohms. I'm using basically logic line drivers or bus buffers to generate a differential signal into this transformer, and a 2-to-1 step up. It gives me a nice clean, square wave 1 watt out. And then let's see, also I ended up developing a 6-channel current limiter, because these things, if you short out the output or even drive them into too low of a load, they just start drawing current. The output impedance it's more like an audio amplifier. Output impedance is really low on these. It's designed to drive a 50 ohm load, but the output impedance is, I don't know, closer to 10 ohms maybe. So if you put a low impedance load on it, these are probably going to overheat. So 6-channel foldback current limiter, designed that, and that feeds run 5 volts into this, and these are designed to run on 5 volts, but they've got some degree of protection from the current with the current limiter. Yes.
So are there 6 of these amps in the Beacon Blaster set?
Yes, 6 of these. And let's see if I don't know if I got a picture here. Oh, well, here's the innards of the Beacon Blaster. This is that controller board I was showing you. Here are the amplifiers. Here's my current limiter and regulator. Put 12 volts in. Puts out 5 volts, which feeds the controller board. The controller board can also be powered just by the USB. It's for configuration, you don't need to power up the amplifiers, but the amplifiers require the 12 volts regulated down to 5, and then current limited. And then these outputs go out. I don't know, do I have a picture of yeah, here we go. This is the Beacon Blaster. We can thank Steve Roberts for this printing out this nice label on his amazing printer. And here are the 6 outputs: the GPS antenna in, the aux splitter output, the 10 megahertz reference, a little blinky light there, a power switch, USB, and 12 volts. Okay, so now we've got 6 square waves coming out. You can't connect, well, you shouldn't connect those to an antenna. You really ought to filter them, and we're going for spurious, better than 40 dB down. That's kind of the US limit. And
So you would be if you did do that, you would be transmitting a fair amount of harmonics, right?
yeah, you'd be transmitting a lot of harmonics. So you need to filter it, and you probably don't want to run 6 antennas. A lot of us, myself included, are using this end-fed antenna. My 80 meters, and up in frequency. It's got a transformer in a box, and then just a long wire. It's got a little loading coil, not too far to kind of make it work better on harmonics on the higher frequencies, I believe. Or low. Anyway, they tune the antenna. It works pretty well for all of the bands we're talking about. SWRs, 2 to 1, or mostly like 1.5 to 1. I think it's as bad as 2 to 1. And surprisingly enough, the SWR is actually pretty bad if you're in between bands, which tells me they just don't have a big resistor dummy load inside the box of the, along with the matching transformer. But it actually must be at least somewhat efficient, because off frequency, the SWR goes up. That tells you there's not a lot of loss. Anyway, so a single antenna, how are we going to feed a single antenna from these 6 outputs? So ended up developing a combiner. This is a 4-channel combiner. It was easy, the first one I did, and designed it using surface mount inductors and surface mount capacitors. And this circuit here is a low pass filter, basically one section, another section, and then this capacitor provides the coupling. So I'll show you related frequency response. But this capacitor then goes through a inductor. So this is its own series resonant circuit. And I have these tuned so that it provides a good coupling between at the fundamental, but it also provides a notch at the 3rd harmonic. Being a square wave coming out here, the 3rd harmonic is the big problem. So I suck out the 3rd harmonic with that and get a pretty good output. Also, the advantage of this filter design is that it's high impedance off the frequency of interest because of the series resonance circuit, which means I can connect multiples of these together in parallel. This is the antenna connection common here, and in this case, I got 4 of these things all tuned to different frequencies, connected at a common point, which then goes to the antenna. The 1 watt square wave goes in here, goes through the filter, and then comes out here. But they really don't interact that much. If I'd used a different type of low pass filter, like a traditional pi network with capacitors to ground, that goes low impedance away from the center frequency, and you'd end up with horrible suckouts. But this topology works really well if you're trying to combine them. So this lets us, in this case, have 4 channels feeding 1 antenna. But hey, that's only 4 channels. So here I go. I made a 7-band combiner, and we got a number of these out in the field now. In order to doing it, it's got a similar topology, actually almost identical topology to that 4-band with the surface mount, but I had to stick some more frequencies in between the 4 bands. The 4 bands I was using were 1 octave apart, so it's pretty easy to keep the filters from interacting. But getting them closer together means I needed higher Q, and the whole Q bandwidth loss thing is a trade-off. And the surface mount inductors just couldn't cut it. I ended up losing too much power if I tried to go with surface mount inductor. So went with hand wound toroids. And this works really well, but it's stupidly expensive because if I had to pay for these, they'd be like $10 each in reasonable quantities and $5 each in stupidly large quantities. So I end up hand winding them. It takes me about 5 minutes to wind each of them, and so I pay myself, $2.75 an hour to make these things because nobody's going to want to pay what they're actually worth. At least that's what I tell myself. Here is the response of these. Turns out I didn't use the that series resonant coupling for suck out. It's just a capacitor to ground in between the sections because the Q of these filters is high enough. You can see here, third harmonic's already attenuated pretty well, so I didn't need that extra notch in the response. So 7-band combiner. These are the 4-band and the 7-band. I'm selling them on the website. So now I compromise. Here's a 6-band combiner using surface mount. I've got 2 of these in operation, one here in Occidental, one in Friday Harbor. And yeah, lose a little bit, maybe a dB worse loss, but works, what's a dB among friends? And it's actually kind of affordable. And so I got 7 channels here, 6 channels here, which nicely matches the Beacon Blaster 6. This port here, I just stuck a 40 dB attenuator. That says 30 dB, but I changed my mind. It's now 40 dB attenuator. So I've got a monitor port. I can connect that up to a spectrum analyzer or something if I want to see what's going on. And so that's going to be available if somebody wants, somebody needs it. Where else? Another thing we needed. So the thing about Turn Island Systems is these are things that either Steve or I need, or somebody else tells me that they need. I'm kind of not really going out and saying I've got this brilliant idea and I've got to sell it to the world. It's more like people come to me and say, "Hey, I've got this problem. Can you help solve it?" So that's how we're coming up with these things. And it has to be anyway. So this is a clock distribution buffer. Got 10 megahertz reference coming out of the Bodnar, let's say, but if you've got multiple receivers, a lot of the people I'm associated with, they've got multiple SDR receiver banks or multiple transmitters. Because they don't have a Beacon Blaster 6, they've got other single band transmitters, and they need a reference for those. Maybe you got a bunch of QDXs. So we got one 10 megahertz clock coming out of the GPSDO, and you want to distribute it. This thing has 1 input, 5 outputs, and you can buy distribution buffers. I've got one. It's an old video buffer that I bought surplus, and it's a rack mounted unit, and other people make these, but I decided what the hey, I've got a nice little metal box here and easy enough. Doesn't require any software like that, so I decided I'd make that. And so I've got a few of these in use. I'm using most of them myself. Okay, getting near the end here. Okay, a lot of these people are using SDRs, SDR receivers, and turns out the front end filter on a lot of them maybe isn't as good as it should be. Depends on what sample rate. Sometimes they'll dial down the sample rate, and so just for power thermal issues, bandwidth on the USB cable, they just don't need that much because they're not going past 30 megahertz at the at the antenna port. But the anti-aliasing filter wasn't designed for that inside the SDR, or maybe it had a crappy anti-aliasing filter to start with. So, and the other thing with SDRs is you connect it to a broadband antenna, and most of the people I'm working with, they've got broadband. They are picking up the entire HF band from 0 to 30 hertz. During this eclipse, some of them were recording, including Phil Karn, recording the entire bandwidth. I forget, I wrote about this somewhere, but using like a 2.7 terabyte, I don't know, a multi-terabyte drive, they can record like 6 hours continuous full bandwidth 0 to 30 megahertz for later analysis. Then they can take the output of that and feed it to whatever analysis tools they want. This is the full spectrum, but that full spectrum includes well, it includes AM radio, it includes other lower frequency stuff, and you really don't need sensitivity at the lower frequencies because, as we all know, because you know, the atmospheric noise is too high anyway. You know, the noise floor, natural noise floor. So it's often a good idea to attenuate the lower frequencies, just to help get rid of overload from AM broadcast, and certainly attenuate the higher frequencies like FM broadcast or police band radios and stuff like that. So I was asked to design a filter like this. It's a shelf filter. Okay, you notice, and it's got switchable 2 shelf filter sections. The shelf filter starts out, in this case, with both sections switched in, it's 20 dB down at 1 megahertz, and then it gradually it rises up. The center point's about 10 megahertz, and then it finally comes to kind of minimum attenuation up to 28 or 30 megahertz. So this green line here is with the shelf filter, and then you can swap these jumpers, move these jumpers over and take out the filters. And here is the low pass, just anti-aliasing filter. So it starts out flat, and then at 28 megahertz, it starts rolling off. And there are 4 sections here. It's an elliptic design or Cower filter, depending on the same thing. So you got notches which help your transition band here, make it sharper. So this thing apparently works really, really well to, if you stick it on the input to your SDR, it really helps avoid overload and aliasing. So selling these, this is probably sold more of these, and these things are pretty cheap. You can go onto the Turn Island System website and take a look. I'm doing this for fun. I'm not doing it for profit, but I'm trying not to at least lose money with every one I sell. I don't mind investing money up front. My time is free, but I don't want to lose money when I ship something out. So I make enough for postage and maybe a little bit extra. Well, more than a little bit, but anyway, it's still a reasonable price. You can take a look. So let's see, anything else? No, okay. And now we come to links. TurnIslandSystems.com, my blog, where I sometimes put other technical stuff, WB6DXE, Steve's, microchip.com. The guys that are doing the Whisper Daemon and doing a lot of the stuff during the eclipse and just general propagation research, check that out, whisperdaemon.org. And then HamSci, which is amateurs radio science. It's run by University of Scranton, I think. And they're really involved with propagation research and the recent eclipse and the upcoming eclipse. Next year, we've got another total eclipse. This was just, I think, annular. So these are cool sites to check out. And I guess that's about it for Turn Island Systems. Oh, yeah. Beacon Blaster 6, it's cool, but there are too many pieces to it. I have to assemble all these little boards, and that made sense for the first wait, stop share, here we go, sorry. That made sense for this. We're figuring out what it needed to do, and arguing about the functions, what went where and what we had to make flexible, what we were pretty comfortable with that could be fixed. So now that we know, I'm going to do a Beacon Blaster 8. And I don't know if anyone's going to need it, but if it's going to be easier to build, probably cheaper to build, certainly cheaper if somebody had to be paid for their assembly time. And it'll actually have better performance because I'm going to be able to improve the way I'm modulating. So I expect the spurs will be even better. And it'll look it'll look prettier. It'll be a slightly smaller box, won't require a rack, won't be rack mounted size. So that's coming up. It's in process. I don't have a schedule for it, but I hope I'll have some available in time for next year's eclipse. So there you go, Turn On Systems. Any questions, fire away.